Okay, chlorine as a side chain, it has an electron withdrawing effect. That means it pulls away some of the electron density of the benzene ring. Okay, so if you compare the reactivity of a chlorobenzene versus benzene, both of them have some sort of electron density above and below the plane, but the electron density in benzene is higher because it doesn't have anything that pulls away this electron density, as opposed to chlorobenzene, where the chlorine atom will reduce the electron density on the benzene ring. And as we know, the reaction of benzenes is electrophilic substitution. Electrophiles usually, they tend to have a positive charge. Therefore, the more negative your electron density is, the higher the electron density is, the stronger the attraction towards the electrophile. Okay, so that's why chlorobenzene is it reacts more slowly with electrophiles compared to benzene. Okay, this effect is the opposite to methylbenzene. Methylbenzene, if you look at the earlier part of your notes, methylbenzene is electron donating, so it acts, it adds extra density onto your benzene ring. So methylbenzene has a higher electron density than the benzene itself. Okay, right. What we're going to look at today is the Fridel-Crafts reaction. This is a type of an electrophilic substitution reaction as well, but there's a specific name for it because Fridel-Crafts is the person who discovered this reaction. Okay, there are two types of Fridel-Crafts reaction. It's the alkylation and the acylation. Alkylation is quite self-explanatory. It means alkyl. Your methyl, butyl, ethyl, these are all your alkyl groups. Okay, basically, if at this point you're still wondering what an alkyl is, basically it's an alkane, but attached as a side chain, not a full alkane. Okay, a full alkane is a CH4, but as an alkyl, it is just a CH3. Okay, so for example, if I show you, so this is an alkane, CH4, this is a methane. Okay, but once if you want to connect this methane to something, then of course you need to free up that one bond to connect it to wherever you want to put it. Okay, so the first reaction, alkylation, is a reaction when you want to attach your alkyl group directly onto the ring. Okay, so this Fridel-Crafts reaction can introduce a side chain into a benzene ring. This side chain can be alkyl or acyl. Now, the second type, acylation. Acyl is not something new for you, but the word is probably something that you have not used before. Okay, so an acyl group is when you have a carbonyl, C double bond O, attached to an alkyl. Okay, so that looks like a, it could be a ketone or it could be an aldehyde. Okay, so if you want to attach an acyl group, okay, of course, one of the bond has to be free. Okay, so that green bond that I've just drawn is the connector between the acyl group and your benzene ring. Okay, so your the green bond is where how the acyl group and the benzene ring is connected. Likewise, here for the methyl group. Okay, right. So how do you, what conditions do you need to attach these groups onto your benzene ring? Okay, so I'll deal with the alkylation first, the alkyl group. Okay, so if you want to attach a CH3 onto a benzene ring, that means the CH3 is your reagent. Okay, however, the reagent must be a halogen containing group. Okay, halogen containing alkyl. So we already know our alkyl, which is CH3, all you have to do is, okay, attach a halogen to it, either a chlorine or a bromine. Okay, choose the reagent. If you want methyl, attach the methyl to chlorine. If you want to add ethyl to your benzene, attach the ethyl to chlorine. Okay, so the reason for that, you will look at it later on when we look at the mechanism. Okay, so this is the reagent. CH3Cl is your reagent. Just like any other electrophilic substitution, you need a catalyst. Okay, a catalyst that is called a halogen carrier. Now, since you have a chlorine here, of course, the catalyst has to match the reagent, okay? You will use anhydrous aluminum chloride. Same catalyst as you would use for other electrophilic substitution reaction, okay? So once you have the reagent, which is CH3Cl, and then you have a catalyst, that's all the condition you need, okay? Remember that it has to be anhydrous. That means not aqueous. It has to be dry. In terms of temperature, at room temperature, this reaction can happen, okay? So what happens is that then you can see that the methyl group is attached to the benzene and you form a HCl, hydrogen chloride, okay? So this reaction can be used to form a methyl benzene or any alkyl benzene, ethyl benzene, propyl benzene, butyl benzene, and etc. How can you do that? Basically, you just change the structure here. Okay, if you want to attach ethyl benzene, if you want to produce ethyl benzene, you just use a chloroethane. Okay, so this red part of the molecule will be attached to the benzene ring. Okay, you must have the halogen. Otherwise, if you don't have the halogen attached to it, then your electrophile cannot be formed. Okay, so I'll erase that since my example is talking about CH3Cl. Okay, next is the acylation. Okay, same thing. Basically, if you want to attach your acyl group, you need a halogen containing acyl. So that means if I want to attach the COCH3, I have to start with a molecule that has the COCH3 and it is attached to chlorine. Okay, so that's my halogen containing reagent, right? The catalyst that I need is also a halogen carrier, which is aluminum chloride. Okay. You can also use other catalysts like iron chloride or iron, but best to use the anhydrous aluminum chloride. Okay, so as you can see in the product, the blue part, COCH3, is attached onto the benzene ring. Okay, so you can look at this too. Right, it's the same blue section of the molecule, and then you form HCl, right? Okay, now we're going to look at the mechanism. We will deal with the alkylation first. Like any other electrophilic substitution, the first part of the reaction involves the formation of the electrophiles. Okay, so if you look at, just refer to your step 1, okay? Keep on referring to your step 1. To form the electrophile, I need my reagent to react with my catalyst. Okay, so my reagent is a CH3 and a Cl. Okay, I try to draw the Cl as a different color. And then my catalyst is AlCl3. Okay, so this is my catalyst. And the other one is my reagent. Okay, what happens in this first step is the carbon-chlorine bond breaks, and then oh, Okay, so I draw the arrow like that, but actually the carbon-chlorine bond breaks. The chlorine will get the negative charge, okay? The carbon will become positive, okay? Remember, whoever gets both the electrons will become negative, and the other person that doesn't get it will become positive, okay? And then the Cl minus will combine with the AlCl3, so you form your CH3. Okay, I don't have enough space. If you can make your handwriting smaller. CH3 plus, that's your electrophile, plus AlCl4 minus. Okay, you now have a minus charge because you're combining a chloride ion to an AlCl3. Okay, so the red one, CH2 plus, is your electrophile. Okay, if you refer this back to your halogenation, it's more or less the same. Okay, the chlorine, one of the chlorine, which is the chloride, will combine with aluminium AlCl3 to form AlCl4 minus. Okay, so the one that we're interested in here is only the electrophile. Okay, later on we'll deal with the AlCl4 minus. Okay, in the next step, of course, that's where the reaction is happening. So we have a benzene ring. Okay, and then we have your electrophile. Okay, the usual happens. A pair of electrons from the delocalized system or the pi system is being donated to your electrophile. In this case, it is the CH3 plus. So you form, hold on. Oops, I meant to use red. Okay, so you form a new bond, CH3. Don't forget your delocalized system is now broken. It only extends from carbon number 2 to carbon number 6 with a positive charge. Okay, because that positive charge came from your CH3, but now it is being spread out over the ring. Okay, if I number this carbon, where your CH3 sits, that becomes carbon number 1, 2, 3, 4, 5, 6. Okay, so your broken delocalized system is now spread out between carbon number 2 and carbon number 6. This is your unstable intermediate. A few things that you need to remember about this intermediate is that carbon 2, 3, 4, 5, and 6 are all sp2. That means the bond angle is 120. Okay, carbon 1 is the only carbon that is sp3 hybridized. sp3 hybridized, and the bond angle is 109.5. Why? Because if you look at carbon number 1, there are 4 electron region or 4 bonds around it. So the shape is trigonal plane. Tetrahedral. Okay, so whilst benzene is a planar molecule, the intermediate is not planar because of that carbon number 1. Okay, so please make sure. I've already mentioned this earlier on, I think in the general mechanism, but I just want to re-emphasize that. Okay, so next step is to restore the delocalization, and the only way you can do that is by breaking the carbon-hydrogen bond and donating the electrons to the positive center. Okay, so electron is negative, combined with the positive charge, it becomes neutral. Okay, your hydrogen is released as a H plus. Okay, so your product is a methyl benzene. You can draw your methyl benzene anywhere, but as I have mentioned this to you, I like to draw my electrophile on that carbon on the top right. okay? The other product is H plus H plus, okay? So nothing new, right? I hope there's nothing new in this mechanism. The last step is the regeneration of your catalyst, okay? So as you can see, the hydrogen, the H plus from this part will react further. H plus react with, if you look at step 1, you see your other product, which is AlCl4 minus, okay? So your H plus will react with that AlCl4 minus. Should have used a different color for this. I'll use a different color. Orange. H plus react with AlCl4 minus. Okay, so what happens is the H plus will combine with the Cl minus. Okay, so when H plus combine with Cl minus, they cancel out, they become neutral to form a HCl. Okay, so this is how you get a HCl from your overall equation. Now, AlCl4 minus, once you have lost one chloride ion, it becomes AlCl3. So AlCl3 is your catalyst, and we have regenerated our catalyst. This is why catalyst is being set, catalyst is set to be unchanged at the end of the reaction. Actually, they change for a bit, but then they are being regenerated, okay? It's not strictly that they don't change at all. They do change, but they go back to the original form, okay? Right, so that's your alkylation. Acylation is no different, okay? So the reason why your reagent needs to have a cool halogen containing is because of this step, okay? If you don't have a carbon-chlorine bond, then you cannot break the bond and you cannot produce an electrophile, okay? A carbon-chlorine bond has a relatively weaker bond. That's why it can be broken, okay? Rather than you use a full methane, CH4, a carbon-hydrogen bond is very strong, not easy to break, okay? Especially if it's a single bond. The next one is the acylation, same thing. Say the acyl group that you want to attach to your benzene ring is a C double bond O with a CH3. Okay, so this is the part that you want to attach to the benzene ring. Of course, the connector must be attached to the chlorine first. Okay, that green bond is the connecting bond. It connects your acyl group, your side chain, onto the benzene ring. Okay, so the same procedure, you react your reactant with your catalyst, AlCl3. The carbon-chlorine bond breaks, chlorine will get the electrons, carbon becomes positive, chlorine becomes negative. Okay, so the Cl minus now combines with AlCl3 to form, maybe I should, okay. So now you form an electrophile, which is your acyl, with a positive charge, okay? And your catalyst becomes AlCl4 minus, okay? Same thing. This is what we're going to attach onto your benzene ring. That is your electrophile. Are you all okay so far? Okay, right, good. It's just that I'm not hearing anything from you, so worried if I'm still talking to myself alone. Right, so moving on to the next step where the electrophile will be attacked by the benzene ring. So from this step, it should be easy. You just follow, okay? So there's your benzene ring. And then there's your electrophile. Just be careful with the connection, okay? Make sure you connect the correct carbon to the benzene, okay? That's why it's better for you to draw it out. Do not connect it to the CH3 carbon, but connect it to the C of the C double bond O, okay? The carbonyl carbon. So the benzene ring will attack the carbonyl carbon that I have left out the positive charge, okay? And then you form an unstable intermediate with a positive charge. There is a hydrogen there. C double bond O, CH3. Okay, so remember that this delocalized system extends from carbon number 2 to number 6. To restore the delocalized system or the delocalization, the carbon-hydrogen bond breaks, the electron is donated to the positive center. So you form your product. And your side product is your H+. Okay? And then to regenerate your catalyst, this last step is optional, okay? If the question asks you to show the regeneration of catalyst, you draw the last step. Otherwise, you can just stop at step number 2, because if the question says show the mechanism to form this product, okay? Then you just stop at producing these 2 products. You don't have to move on further where you show the catalyst is being regenerated. But if they do say to show the catalyst being regenerated, then of course you have to add on an additional step. Same thing, which I will not explain because it's basically the same explanation, plus AlCl3. Okay? Right, so that's your Fridel-Crafts alkylation and acylation. You can imagine how you can play with the number of carbon atoms on the alkyl group of your acyl, as well as the number of carbon atoms on your alkyl group. Okay, it depends on what your desired product is. So you just have to play with your reactants. Remember, your reactants must be attached to a chlorine. Otherwise, if it's not attached to a chlorine, then this production of electrophile cannot happen. Okay, right. So the last 2 mini reactions of benzene that we're going to look at is the complete oxidation of the side chain to give a benzoic acid. Okay, so here we have methylbenzene. Okay, as we know that methane cannot be oxidized, right? However, but when you have an alkane attached to a benzene, so that means it's an alkyl arenes or alkyl benzene, okay, this CH3 group can be oxidized to carboxylic acid. Okay, so I'll talk about that first. Alkanes are not usually oxidized by a chemical oxidizing agent such as potassium manganate or potassium dichromate. Okay, but alkanes on benzene can, right? Alkyl arenes means the alkane group or the alkyl group that is attached to a benzene ring. Okay, remember, arene is the group that your benzene belongs to. Benzene is the simplest type of arene. So this is what we call an alkyl arene. So if you look here, this is an alkyl. And then the ring is called an arene or benzene ring. That's why we have an alkyl arenes. So in alkyl arenes, the alkane side chain is oxidized to form a carboxylic acid. Okay, so what happens is that this CH3 turns into a COOH. Okay, you don't need to know the mechanism. It's something that you just have to memorize, right? So the oxidizing agent that we use is potassium manganate, alkaline potassium manganate. Okay, so you alkaline potassium manganate and you heat it in reflux, right? That's your first step. The second step, then you acidified it with dilute sulfuric acid. Okay, please do the step 1 and step 2 separately. Do not write down alkaline potassium manganate acidified acid, because what happens is the alkaline and the acid will just neutralize each other. Okay, the reason why we write down step 1, step 2 is because you do step 1 first and then followed by step 2. You cannot mix step 1 and step 2, otherwise it's just neutralization of the alkaline and the sulfuric acid. Okay, so how do you write the equation? Basically, you just have to balance the equation. Oxidizing agent is represented as a square bracket O, because when something is oxidized, it gains oxygen. Okay, so COOH and water as the product. Okay, and we call this product a benzoic acid. Okay, the next section you will see that interestingly, any alkyl group is oxidized back to a carboxylic acid group. Okay, so it's not just your methyl group. If you use propyl, butyl, what else? Octyl, decyl, etc. As long as it is an alkyl group, it will be oxidized to a single COOH. Okay, but we don't look at the equation because obviously it's a little bit harder to balance out the equation. Okay, so just remember, when you have an alkyl attached to a benzene, you treat it with an oxidizing agent. It can be oxidized, whatever alkyl it is, it will be oxidized to the same benzoic acid. Okay, and this is only applicable when you have an alkanes attached to a benzene ring. Alkanes alone will not be oxidized by oxidizing agent. Okay, so same condition. You first use alkaline potassium manganate, so that means sodium hydroxide mixed with potassium manganate. And then after that first part is done, then only you add the dilute sulfuric acid. Okay, that's oxidation of alkyl benzene to give a benzoic acid. The last reaction of this topic is the hydrogenation of your benzene ring. Okay, hydrogenation means you are adding hydrogen onto your benzene ring. Now, sometimes students get confused because they forget that these benzenes contain hydrogen, one hydrogen already. Okay, as you add hydrogens to it, the double bond inside the ring will break. Okay, so the hydrogen is the original hydrogen I'm drawing here. So when you hydrogenate it, if I use a red one, you will get that. Okay, the red hydrogen is the hydrogen that comes from the reagent. Okay, the catalyst is a nickel catalyst and 150 degrees temperature. I think this is quite standard, a standard condition for a hydrogenation process. Okay, so you form what we call a cyclohexane. You are breaking all the 3 double bonds inside the ring. Okay, and since you are adding six hydrogens, that means you need 3 H2 molecules. Okay, for this second example, I will draw the original hydrogen H, H, H. Okay, now the carbon where your methyl group is sitting no longer has the hydrogen. Okay, the hydrogen has been substituted already. So your product, you are only adding, you are actually adding 6. 1, 2, 3, 4, 5, 6. Don't forget that carbon, okay? That carbon number 1. Take note of that carbon number 1 where it is holding a methyl group, but an incoming hydrogen can also come in, okay? So that means you are also adding 3 molecules of hydrogen, and this is called a methyl cyclohexane. Please take note that the cyclohexane is no longer a benzene ring. It is now an alkane. Okay, change of functional group already. It is not a benzene ring anymore because you have completely broken the delocalized system. Okay, so these reactions destroy the electron delocalization in the original benzene ring because those electrons are being used to form bonds with the new hydrogen atoms. Okay, so please take note that cycloalkane is no longer a benzene or an arene functional group. Okay, right, so that is all for this topic. We're done. I will do a few sessions of doing questions, exercises together, but you need to take out your AS notes because some of the questions are usually mixed. Okay, I've already sent you exercise 15.1. Is this topic 15? Yeah, exercise 15.1. So if you haven't printed that out, please print it out. If you cannot print it out, I think I have 1 or 2 copies that I left in school if you want to take it, okay? And then I'll get your notes ready for the next topic, which is phenol, topic 17, I think, if I'm not mistaken. Okay, you have less than 4 minutes left. Do you have any question to ask before I end this session?
No.
No? Everything okay?
Yeah.
Can understand this topic?
Can.
Okay, good. I hope that applies for everyone as well. Right, if you do not have questions,